Good morning, everybody, and welcome back to Math 115. So today we're going to continue on with Chapter 1. So we already kind of discussed, this should say 1.5/1.6, shouldn't it? 1.5/1.6. That is what we're going to talk about today. So we have kind of moved into talking about functions, so we're going to talk more about functions today. So 1.5 considers properties of functions, and then 1.6, I think, is building a library of known functions that you can draw on. So that's going to be what we talk about today, but before we talk about that, let me remind you that there is a homework assignment. It actually was due last night, but I had a lot of people email me because they were confused because last time during class we kind of talked about, well, maybe I would extend it one day, but then we didn't really decide, so I extended it. It'll be due tonight at 11:59 p.m. So if you didn't do the homework that was due yesterday, you got another chance to do it today. Is everyone okay with that? Okay, cool. All right, and then 1.5 is going to be due on Wednesday. So what that means is that the homeworks, which are after our last exam but before this coming quiz, are just sections 1.4 and 1.5. So that's all that you need to prepare for the quiz this Thursday. So the quiz this Thursday is going to be on sections 1.4 and 1.5. Homework 1.5 is due Wednesday. Homework 1.4 is due today. Other than that, I have graded the exams, and I was really happy, generally, with the way that they went. I think that we had a pretty excellent average, and then also I really enjoyed all of your responses to the bonus questions. So thanks for taking the time to write those out. I really appreciate that. Two more things. My office hours are going to be again this week, as they are every week. Tuesday, Thursday from 2:30 to 4 in my office, LeConte 439. If we have a lot of people, we might move, but I'll put a sticker on the door. So in particular, if you want to perform well on Quiz 3, there's an office hour tomorrow from 2:30 to 4 that it'd probably be a good idea for you to attend. If you can't come to my office hours, then there's this other resource which is super useful, the Tutoring Center in LeConte. I had some people ask me, how does that work? What do I have to do in order to go to the Tutoring Center? Do I need to sign up? No. You just go, and then you sit down, and someone will be there, and they'll come and help you. So all you have to do to get free math tutoring from another math PhD student like me is go to this room, LeConte 102. Just show up. Anytime between 10 and 4 on Monday, Tuesday, Wednesday, Thursday, or between 10 and 1 on Friday. I really can't overstate how useful that resource is. It's super available with your schedule, and it's going to be super helpful in terms of like really high caliber instruction. So I can't recommend that enough. And on the exam, I'm going to pass the exams out tomorrow probably, because I still have a few people who need to take the exam that are taking it in my office after class today. So I'll pass them out hopefully tomorrow. Any questions on the exam or homework or anything administrative in nature before we start in on content for today? All right, it doesn't seem like it, so let's jump right in. Well, actually, let's not jump right in. Let me remind you what we learned last time. So last time we finished 1.4. So what did that entail? That entailed learning about the vertical line test, okay? So moving your pencil back and forth. Does it touch at 1 point or 2 points? If it ever touches at 2 points, then it fails the vertical line test and hence is not a function, right? So that was the vertical line test. We also learned a little bit more about domain and range, okay? So this was a piecewise function where we learned how to, first of all, we learned how to write down piecewise functions, and also how do we figure out the domain and range from looking at the graph? Well, the domain is what's going to show up on the x-axis, right? And then the range is going to be all the possible y values that can be attained by the function. And then we had this practice problem, which was just a bunch of stuff about plugging in to functions, finding the points on a function, finding intercepts, and then domain and range. So the other kind of useful thing that we learned about that was that the vertex of a quadratic function will always be at this point. Okay, so if you just memorize, really you don't need to memorize this entire point. What's the only thing you have to memorize, really? Do I need to memorize both negative b over 2a and f of negative b over 2a? No, just negative b over 2a is enough, right? Because how do I get the y value of a function? You take the x value and do what to it? Yeah, we plug it in, right, to the function. If you take the x value and you plug it into the function to see what we get, that's how you know what the y value is going to be on the graph of the function, okay? So really just remember negative b over 2a. That's the x value of the vertex of a quadratic. Okay, then we talked about classifying some functions, so linear functions, quadratic functions, polynomial functions. We already talked about polynomial functions, I think, at some other point. Right? We did that in like the first week or something. Am I crazy? Sometimes these different classes blur together. Okay. And power functions, okay, where the difference between power functions and polynomials is power functions, we allow the power to potentially be a fraction or negative or something like that. All right, so that brings us to 1.5, which is when we started talking about properties of functions. So far we've only really handled 3 properties. We have the property of being increasing, the property of being decreasing, and the property of being constant. And I think that's it that we did last time. Okay, so for increasing, what does it mean? It means if I have 2 points, 2 x values, and one of the x values is to the left of the other x value. Okay, so something like x1 and then x2 is to the right. Okay, then what should be true about the points at x1 and x2 in terms of their height? Well, if we are an increasing function, then the height of the point on the right should be what? Higher or lower? If we're increasing, it should be higher, right? That's the whole point. We're increasing from left to right. Okay, so if we want to have an increasing function, then this should be true for every 2 points which are between a and b. So I've got a on the left, I've got b on the right, and f is increasing on the interval from a to b if for every x1 and x2 that I can choose. Okay, for example, I could choose this one and this one. Or I could not choose those. I could choose this one and this one, right? Any 2 x1 and x2 inside of the interval with one to the left of the other, then we have this increasing property happening. Okay, so same for decreasing, except of course we should be going down, right? And then constant, what should we be doing? Just staying the same, right? We should just be not going up and not going down. Okay. Any questions on any of the topics which we discussed last time? Okay. If not, then we'll do something different today, and we'll jump right into a partner exercise. Okay, so our goal for this problem is to use interval notation, okay, to determine the set of x values for which f is either increasing or decreasing or constant. So I want 1 for increasing, 1 for decreasing, and 1 for constant. And you're going to notice that there's multiple places where this function is increasing or decreasing, right? So if we're going to describe the set of all x values for which we are increasing or decreasing on that set, then we need to use, of course, a union, right? Okay, or an intersection, depending on what we're doing. Okay, does everyone understand what we're going to be working on with the partner? Okay, then go ahead and get started. I'll float around and help as necessary. Hopefully my drawing's good enough.
What is the top number? What does it go up to on the y-axis?
On the y-axis? I guess it doesn't really matter, but let's see. how about we make it, I don't know, 2? Is that good? And then we'll make this one -2. That looks like about right. Okay, so for instance, we're trying to describe X value or width. So in particular, the Y value goes all the way which X so where are you talking about? I'm guessing you're talking about the point going from -3 to -2 up to looks like 2, right?
I literally some of these functions I wrote less. I had 3 minutes to do 2.
Well,
I know. Because I like.
Trick question. So if there's I don't have to worry about it. That's perfectly fine. Two. And then it looks like we're constant. And are there any other ways we are Let's see. Increasing from -3.
Yeah, like I put so much.
Increasing -5 to -3 and 5 is set there. I've got a constant on 2 to 5. Yes, except one thing that we should probably use is
There was another
not open brackets.
I don't think since this is like very appreciative of every time that it's not 5 million.
It will matter. Let's discuss it.
That it's like this card.
Okay, would anyone like a little more time to work still? Or are we ready to talk about this? Okay, then let's talk about it as a group. Okay, so let's start by maybe highlighting the part of the graph which is going to be relevant for the increasing part, right? Well, where does it look like we're increasing? Well, increasing means as I go from left to right, I'm going up, right? That's what increasing means. So from -5 to -3, does that count as increasing? No, because if I was walking on this hill, would I be going uphill or downhill? I'd be going downhill because we're always moving to the right, okay? I'd be going downhill, so that's decreasing. But then it looks like we are increasing on this region. Agree? Okay. So I want to describe all of the x values of the points at which this function is increasing. So what are those x values going to be? I should go from -3 up to 2. And let me ask you a question. What about at -3? If I just consider a single point, is my function increasing at this point? I'm hearing some scattered no's, which is the correct answer, and I'm wondering if anyone can explain why. Gavin?
Because begins to progress after 3 instead of like on the dot. That's going to be like a certain, it's going to be like -3 to -2, I think. So.
Yeah, that's a good intuitive way of describing it. So what Gavin said was it doesn't start to increase until after you hit this point. So if you think about it in a certain kind of a way, here's another way to think about it. Imagine I was riding a roller coaster. Okay, that's not a good roller coaster boxcar, but here I am having fun on this roller coaster. And this part I'm going down, right? You can tell I'm going down because which direction am I facing? I'm facing down, right? How about after that? Well, over here you can tell that I'm going up. Why? Because what direction am I facing? I'm facing up. But ask ourselves, what direction would we be facing at the second that we hit the bottom of this curve? We'd be facing dead straight ahead, i.e. not up and not down. So I wouldn't necessarily go as far as to say that I'm constant at the point -3, just because for us to be constant at that point, we would need to be constant on some small neighborhood of that point. So we can't say that we're constant. In fact, what we're going to say is that we are increasing from -3 to 2 with parentheses, okay? And we're going to say we are neither increasing nor decreasing nor constant at the point -3, because what we're going to say is we were decreasing from -5 up to -3, okay? So decreasing, and then I'm not doing anything for a split second, and then I'm increasing, and then what am I doing? Then I'm constant from -2 up to, sorry, not -2, but from 2 up to 5, right? Okay, and then what about this last bit? Decreasing. How am I going to incorporate that into my answer? I'm going to use a union, and then here comes 5, 7. Okay? All right. So, how do we feel about that example? Pretty good? All right. Yeah, I think the only sticking point for this one was really just, okay, what about the points where we change from being one of these to being the other? And what you have to consider for that is what the definition says. The definition says we are constant on the interval from A to B, where this is an open interval, okay? We can never be constant or increasing or decreasing at the edge of one of these intervals in this kind of way. If you look to the right of this point, we are constant. But if you look to the left, we are increasing. So what am I doing at this point? It's not clear, right? So we don't include it in our answer. Are there any questions about that? Okay, then let's move on. All right, so the next one that I want to talk about is what it means for a point X to be a relative maximum or a relative minimum. Okay, so what do we say? Let A in X. What does this mean? This just means that A is a value in the domain of the function, okay? So nothing crazy there. All we're saying is, okay, look, A can be plugged into the function. Okay, then what? Then f of A is called a relative maximum of f if one thing is true. What we need is, and this is a very technical definition, okay? This is a very technical definition with an extremely simple idea behind it, but let me give you the technicalities. There needs to exist, okay? Meaning I can find an interval, okay? x1, x2, containing A, okay? Sometimes we call this a neighborhood of A. You can learn all about neighborhoods if you take a class on topology one day. But anyways, there exists a neighborhood or an interval containing that point, okay? So what does that look like? So if this is the point A, then the interval containing A would be something like this. Here's x1 and here's x2, right? So we need to find an interval containing A, could be really, 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 really small. But what needs to be true is that for every other x value in that interval, we have that the height of the function at A is larger than or equal to the height of the function everywhere else in the interval. Okay? So what does that look like? Well, it looks like the following. This is the point A comma f of A, right? So you can see this is the height f of A, right? So what is true? Well, it's getting really hard to see because my pen is not small enough. Oh, I guess I can make it smaller. Okay, if I take any other x value in here, right, what's going to be true is that the height of the point corresponding to that x value will be less than the height of the point corresponding to the x value x is equal to A. Okay, so what does it mean? It means that I've hit a peak, basically, of my function. I hit a peak, right? How do I know when I'm at a peak? Well, I know I'm at a peak if no matter which direction I go, I'm going down, right? That's how I know I'm at a peak. Okay, if you're talking about x values, there's only two directions to go. If I move to the right, I'm going down. If I move to the left, I'm going down. Loosely speaking, that means that there's a small interval such that if I'm in that interval, A is the tallest possible point on that interval. Now, why do I specify that it needs to be an interval about A, right? Instead of just it's the tallest point of the function. Well, we're talking about a relative maximum here, okay? A relative maximum can be juxtaposed with another type of maximum, which we call a global maximum, right? Which can be seen here at the tippy top over here, okay? So this point here is known as a relative maximum. This point here would be known as a global maximum, okay? Which global maximums are always relative maximums. Not so in the other direction. Relative maximums may not be a global maximum, and as is the case for this one. Okay, so that's a really technical definition for a super simple thing to grasp intuitively. Any questions on that definition? Okay, how are we going to modify this definition in order to discuss a relative minimum? How would I change this definition to get not a relative maximum, but a relative minimum? Anything I need to change?
It would just be f of A is less than or equal to f of x.
Exactly. All we would do is we would replace this guy with a less than or equal to, okay? We want it to be the smallest possible y value on that subinterval. Okay? So I didn't write that out, other than I wrote for relative minimum, just replace the greater than or equal to with the less than or equal to. Okay, so how do we actually find it? Well, if you want to find relative max, okay, relative maxes, I guess, so we could have multiple. Find relative maxes on graph, you just look for the peaks, okay? And if you want to look for the relative minimums, you look for the valleys, okay? So peaks and valleys, right? It's super useful to be able to understand where is a function at a maximum or a minimum. Because what if this function is describing like our profits or something like that, right? If I am a business person, then my interest is in maximizing profits and minimizing losses, right? So if I have functions which describe those, then I want to find the x values which are going to maximize or minimize my profit or loss. Okay, so one thing on maximums and minimums is that it's really easy to find them when your function is quadratic, right? When your function's quadratic, then it's really easy to find the maximum or the minimum because it's a parabola, right? It's only got one, and we know exactly where it's at. It happens at the vertex, okay? So why do I specify if A is larger than 0? then the maximum of this function is going to be obtained at the vertex. Why do I specify that a should be positive? And also this should be minimum. God. Minimum, sorry. That's probably why you're so confused. Exactly, because if a is positive, what does that tell us about our parabola? It opens up, right? That's what happens if a is positive. If a is negative, how is it going to look? Well, there's only two options, right? It's either up or down. So if a is negative, then it opens down. So you understand why if a is positive, we're going to have a minimum value. And if a is negative, then we're going to have a maximum value. Yes? Okay, and in both cases, it will be obtained at the vertex. Okay, so let's see an example. All right, well, f of x equals x squared plus 2x plus 1. If we wanted to graph this, what would we do? Well, we could do it in a couple ways. We could use the formula to figure out what the vertex is, or we could factor this. I know that this factors as x, plus 1, and x plus 1, yeah? So if I set that equal to 0, and that tells me that x is equal to negative 1 is a double root. Right? What does a double root mean? It means that our parabola is going to come down to x equals negative 1 and touch it there and then go off. So if I draw this graph, I don't even really need to do negative b over 2a. But if I did, what would I get? I'd get negative 2 over 2, right? Which would be negative 1. And then f of negative 1 would be negative 1 squared minus 2 plus 1 is 0, right? So you can find it in a couple different ways if you want. I like the graphing way because you get to see what the whole picture looks like. So x equals negative 1 corresponds to a minimum, namely f of negative 1 equals to 0. That is the minimum value. And why is that useful? Well, that's kind of useful when we're doing parabolas, because now what can I describe easily? I can describe the range very easily, right? The range of this function is going to be from 0 up to infinity, okay? Any questions on how I did that? Yeah.
If something, like for another problem, if it's a double root, does that automatically means the vertex? If there is a double root, does that automatically mean that's the vertex?
Yes. Yes, it does. But actually, no. Not if... Wait. Okay, yes. If you have a real double root, it's definitely going to be the vertex. But as you know, you can have... Well, as you may know or may not know, you can have parabolas which look like this, in which case there are no real roots. There are complex roots. So you could have a double complex root, and if I'm right, I think that would look something like this. Okay, in which case the vertex is going to be at 0 and have some kind of positive value. But I wouldn't worry about that. What's important to know is that if you have a double root, what does that mean for the graph of your parabola? If you have a double real root, it looks like this, and it touches, and then it goes off. Okay? Because otherwise, we would pass through, right? And then if we pass through, then there's got to be another root, right? All right. So not so satisfying answer to your question, sorry. Any other questions? All right. Okay, so like I said, if a is a negative number, then we are going to have not a minimum, but a maximum. I got these mixed up. we will have a maximum, not a minimum. Right, because a less than 0 looks like that, yeah. Okay. So next up, we're going to talk about two new properties. So we already talked about increasing and decreasing and constant. And we also talked about where a function has a maximum or a minimum. And now we're going to discuss whether a function is even or odd. And you might think, well, that's kind of weird, because I know that numbers can be even or odd. But what about functions? Well, it turns out functions can also be even or odd. We just have to come up with a new description of when they will be even or odd. Okay. So the new description for when a function is going to be called even is that f of x should be equal to f of negative x. Okay, what does that mean? That means that if I take x and I plug in negative x and x, then the height of the function at both of those 2 points is the same. Right? Is the same height. Okay, if I have a function which satisfies this, then it's going to be symmetric about the y-axis, right? Because symmetric about the y-axis was that if xy is on the graph, then negative xy is also on the graph. Well, xy, y is f of x, and we know that f of x is the same as f of negative x. So yes, this is going to be true by virtue of this equality. So let's see, an example would be something like f of x equals x squared. Let's see if I can draw a good one. Okay, come on, move now. There you go. Okay, so something like this. So as you can see, x, negative x, f of x is equal to f of negative x. Okay, so the height of this point is the same as the height of that point. All right, so why do we call them even? Well, we call them even because power functions with even roots, not roots, even powers are even. For example, x squared, x to the 4, x to the 6, okay, x to the 8, they're even functions. And it also just so happens that they have even powers, okay? It's not necessarily true if we have a mixture like x to the 4th plus x, okay? This is not going to be even just because there's an x to the 4 here, because we've also got this other thing here. And what's the power of this guy? It's 1, and 1 is odd. So this is a function that actually would be neither even nor odd.
If we're like x4 plus x squared, would that then be even?
Yes, a sum of two even functions is also even. You can, it's clear why, right? Because, okay, if f1 of x equals f1 of negative x, yes, and f2 of x equals f2 of negative x, right? If this is true, then what is going to be true? f1 of x plus f2 of x, you just add these two equations together, is going to be equal to f1 of negative x plus f2 of negative x, right? So yeah, a sum of two even functions is still even. That's a great question. Any other questions? All right, so we talked about even, now let's talk about odd. Well, if we have an odd function, then something else is going to be true. Okay, so we're not going to have f of x equals f of negative x. It looks a little different. What's the difference here is before we had the negative sign was inside of the parentheses, and this time the negative sign is outside of the parentheses, right? That's the difference between the two. So this says that the height, and also this needs to be a negative sign in here. God dang it, I made another mistake in here. Well, at least I'm catching them as I go. This should be negative x. So what does this say? This says that the height on the left side needs to be negative of what it is on the right side. Okay, so if I have x, and then here's negative x, if this is the height f of x, then what does the height of f of negative x need to be? It needs to be negative of whatever the other one is. So its height would be down here. Okay, so what does that mean? Well, it means that we're going to be symmetric about the origin. Okay, so you could take, for example, the function f of x equals x cubed, which looks something like this. Okay, and you can tell that for every point that I have on the positive x-axis, if I go that same x value on the negative x-axis, okay, then the height of that point is going to be negative of whatever it was on the right side, okay? So this is our symmetry about the origin, okay? And yes, it's also true that power functions like x cubed, x to the 5th, x to the 7th, they're all odd. Okay. Any questions on even and odd functions? Let's see an example of how we actually figure it out. There's basically two ways to figure it out. The first way is to look at the graph. If you have the graph, you can identify, you can just look at it and say, well, it does certainly look symmetric about the origin or about the y-axis, right? But what if I don't have a graph, and also I don't know what the heck that function even looks like? Okay, I don't even know what this function looks like. Then here's how you check. You check for evenness by plugging in. What should be true? F of x should be, we're trying to check this equality, should be equal to f of negative x, if it's even. So we're going to see, is this true? If so, we know it's even. So let's try. Well, if I plug in x, I just get x cubed minus 4x. And what do I get if I plug in negative x? Then I get negative x quantity cubed, remember to plug with parentheses here, and then minus 4 times negative x. Right? Minus 4 times negative x. So what is that when I simplify this? What do I get when I take negative x and cube it? Negative what? X cubed, right? Minus. Or is it a minus? It's a plus, right? 4x. Okay, so our whole goal was to figure out whether this is true or not. And it seems like definitely not, right? These two are not the same, are they? Do they have another kind of relationship, though? Yeah, the one on the right is the negative of the one on the left, right? So I think we're going to start to check for oddness. We want to check, is f of x equal to f of negative x, but negative? That's what we're going to check now. Well, I can repeat this calculation on the right-hand side easily. I just need to, of course, add a negative sign on all of this. Which is going to be equal to x cubed minus 4x. And then the left-hand side is exactly the same. Nothing changes. I probably should have copied that, not dragged it. So let me move this back up really quickly. Copy, paste. Get rid of those. And get rid of that. Okay, so that was not even. But look what happens when I do the oddness check. Well, what I do when I do the oddness check is I get, okay, whatever the negative thing was inside, but of course the whole way through I'm carrying this negative sign. So at the end, I'm going to distribute that negative sign onto these two terms, and I will get positive x cubed minus 4x. And the whole goal here was to check whether this equality is true, and I say, yes, it is true. Okay, so now the function is odd. So conclusion. F of x equals x cubed minus 4x is odd. Okay? So what's going to happen if a function is not even and not odd? Well, this sometimes happens, okay? It's not true that a function will always be either even or odd, right? So if we check evenness and we're like, oh, no, it's not even, it didn't work. And we check oddness, and then again, not like this example, but if we got no again for both of these questions, if we had both of those, then we would say neither. Okay? All right, that's even and odd. Any questions on that? All right. Then let's talk about average rate of change really quickly. Okay, so average rate of change is, I think, a more complicated notion. Okay, is a more complicated notion, especially if you want to talk about it without using the language of calculus, which obviously we're going to do because we don't know calculus yet. So what is the average rate of change? Well, let's give the definition and then let's see how it's explained. Okay, so the average rate of change, which I usually write AROC, of a function over an interval. Okay, so I take a function in an interval and I want to check what is the average rate of change. It's defined to be f of b minus f of a over b minus a. So let's see what that looks like. If we have f of x equals x squared, let's take a look at the graph. Looks something like this, right? And I want to find the average rate of change over the interval from 2 to 4. So here's 2. And of course, this right here is the point what? 2 comma. What would be the height of this point? It would be 4. And how do I get that? I take 2. And I plug it in for x here. So that would be 2 squared, which would be 4. So I know this is the point 2 comma 4. And how about if I plug in 4? Let's see what the height is going to be. It's going to be 16, right? Okay, so this is just graphing functions. Nothing crazy happening here. But what is this thing? This thing is weird. Does this formula remind you of anything? I guess it's written on the right-hand side, right? Should remind you of the slope formula a little bit, right? This kind of looks like y2 minus y1 over x2 minus x1 is kind of what it looks like. So what is f of b minus f of a over b minus a? In this case, this is our a, and this is our b, and f of a is 4, and f of b is 16. So we get 16 minus 4 all over 4 minus 2, which is, of course, 12 over 2, right? And that's 6. Okay, but what the hell is the point of finding that? That doesn't make much sense because this function isn't a line. Why are we doing a slope when this is not a line? Well, this is the slope of the direct path from a f of a to b f of b. Okay, so it looks like this. Okay, if you were to draw a secant line is what this is called. Okay? All right, so this is the average rate of change. Now, as for why we care about this, it's maybe not as clear until you learn calculus. But let me see if I can give a high-level description. Okay, so let's say that f of x is describing my distance from home, right? Maybe my distance from home, okay? So I start at home, right? And then the height of my function is 4 here, so I'm 4 miles away from home, right? And then later on, I'm 16 miles away from home, right? Because that's the height of my function, right? So in this case, we might want to describe from the distance function how fast we were going, right? And since this is just the height of the function is describing distance, then the steepness of our function will describe the speed at which I was traveling, right? Or my velocity, right? So what does this line have to do with that? Well, it's really hard to measure the steepness of this function at a particular point. What's easy to do is to draw this secant line. And I know this secant line is roughly speaking kind of how fast I was going in this region, because the steepness of this secant line is really similar to the steepness of my function in this region, right? So this would describe, okay, how fast was I traveling from hour 2 to hour 4 on average? Well, I started at like a certain mile per hour and I ended going somewhat faster, right? But if I ask myself, how fast was I going on average during that time? Then that's something that this average rate of change computation could help us to discover. All right, but let me just reiterate, I won't expect you to know anything about that velocity stuff or that distance stuff. This is just to help motivate why we might want to know what the average rate of change of the function is over an interval. Okay, so here's another example of a graph, just so that you can see a little bit better, because it's hard to see with this one. But maybe our graph looks something like this, okay? And then you could say, what is the average rate of change from A to B, right? Well, here's B f of B, and this is A f of A. Okay, what is the average rate of change? We just draw this line and we check the slope. Average rate of change equals slope of this line. Okay, to find the slope of that line, you know 2 points on the line. Just subtract the y values and divide, then subtract the x values. Okay, any questions on average rate of change? Okay, let's do one more example of average rate of change, and then we'll finish for today. Let's find the average rate of change of x cubed minus 4x over the interval -3, 3. Does anybody recognize immediately how I'm being sneaky with this problem? Well, this is the function that we talked about earlier, which was odd, right? Let's see how that's going to play into this. Okay, let's see how that's going to play into this. All right, well, let's see. What do we have to do? We have to do f of b minus f of a all over b minus a, right? Which in this case is going to be 3 cubed minus 12 minus -3 cubed plus 12, right? All over 3 minus -3 is 6. Okay, so 27 minus 12 is 15, right? And then -27 plus 12 would be -15, right? Hang on, -27 plus 12, yes, would be 15. Okay, so what do we get in the end here is 30 over 6, right? Which is just 5. Okay, so I ran out of time. I won't do a graph, but that's how we do it algebraically. Yep, have a good day.
You too.